Sorry, guys, I didn't write that down because I mean essentially I just said the answer, but hopefully you can remember what was being said there. If you want to like sort of try to confirm answers with me, we can always do that over email, by the way. So for so it's not as awkward to say it in front of the whole class.
Do you have recommendations on starting 4A or B?
4A or B. So I would use um, the domain of numbers, like all.
Don't make it too
possible.
complicated.
It's easier when you do it that way. So I mean, what's this saying here? I mean, just think about it in your mind for a moment. So we're looking for a interpretation in which these things are false, both of them. Okay, and we're not interested really in interpretations where they're true. You can always construct an interpretation in which something is true. The real hitch is when, are they false sometimes? Okay, so how do you make it, and these are both implication statements, how do you make an implication false?
The hypothesis is true, and then the conclusion is false.
Mm-hmm. Remember, the only time an implication is when the hypothesis is true and the conclusion is false. The only time an implication is false is when the hypothesis is true and the conclusion is false. What if the hypothesis is false?
It's true.
What's true?
The implication
The implication is true. What about the conclusion?
doesn't matter.
Irrelevant, yes. When the hypothesis is false, the conclusion is completely irrelevant. It could be true, it could be false. Right? And therein lies a logical fallacy that is pervasive. When people, it's pervasive throughout humanity. When people want to, want to talk, sometimes they say, well, we know this is true, and therefore we argue from here and come to some other conclusion. And then, well, maybe you don't like the conclusion. Like, that conclusion can't possibly be right, so their argument must be wrong. Well, actually, their argument has nothing to do with it. Their argument may be just fine. The problem is they supposed something right at the beginning in their hypothesis that was just false. And when you suppose something false, it doesn't matter what the conclusion is. The implication that they're making is going to be true. Okay, so whenever people say, well, everybody knows this is true, think about it a little bit more. They'll think about it a little bit more, and maybe it's not quite true.
What? What?
Can you hear me? Sorry?
Yes.
Okay. Were you talking to us, or you need to switch your mic off, maybe? All right. So in both of these statements here, they're both implications. So we want to get an interpretation in which they're false. So you've got to make the hypothesis true and the conclusion false. No problem. No problem. Happens a lot. All right, you've got to make the hypothesis true and the conclusion false. So, for simplicity, you might want to use the domain just positive integers, right? Or maybe I'm not saying you have to. You can use the whole universe if you want, or some other domain. But you gotta have to really be careful about what you're going to say. So you must make the hypothesis true and the conclusion false. So you have to think of a meaning for P, think of a meaning for Q, which makes this true, but that false. Okay. So what's this saying? For everything in the domain is either P or it's Q. Everything in the domain is either a potato or a queen. Right? Everything in the domain is either a potato or a queen. That implies everything in the domain is a potato or everything in the domain is a queen. Well, what would make this true and that false? Everything in the domain is a P or everything in the domain is a Q. Yet everything in the domain is either P or Q. What would have to be the case with P and Q to make this true and that false?
There would be no P or Q.
Well, that would make this false.
Oh.
Don't want. That's got to be true. Everything in the domain must be something that is a P or something that is a Q. Odd or even, say, right? P means odd, Q means even, or something like that. Well, that means everything in the domain is odd, or everything in the domain is even. That's false, right? As long as P and Q, everything is either in P or Q, but like there are things that are P's but not Q's, things that are Q's but not P's. Right? Every living thing is an animal or a vegetable. Therefore, every living thing is an animal, or every living thing is a vegetable. No, right? I mean, not. I know what I said is false there. Every living thing is an animal or vegetable. There's things other than that, right? Prions and other weird things that you wouldn't know about. I wouldn't know about. Maybe you do. Okay, every living thing is an animal or a vegetable. I mean, it's not really true, but say it is. Therefore, every living thing is an animal or every living thing is a vegetable. That's false, right? So as long as P and Q don't cover everything, but not everything is a P or not everything is a Q. Like you don't want to say something like this. Well, every living thing reproduces or drinks coffee in the morning. Right? Every living thing reproduces or drinks coffee in the morning. Therefore, every living thing reproduces. Well, yeah, that's true. This is true and that's true. So the implication is true. So you want to make sure P doesn't cover everything, Q doesn't cover everything. Okay, what about this? There exists something in the domain that is P, and there exists something in the domain that is Q. Therefore, there exists something in the domain that is P and Q. So you must make this true and this false. There exists something in the domain that is P, and there exists something in the domain that is Q. Therefore, there exists something in the domain that is P and Q. Well, that won't be true when P and Q are mutually exclusive, so to speak. Right? There are some living things that are animals, and there are some living things that are vegetables. Therefore, there are some living things that are both animal and vegetable. right? That's false, right? Some living things are animals. Some living things are vegetables. Therefore, right, there is a living thing that is an animal and a vegetable. The blue-green algae or something. Maybe that's both, but I mean, you know what I'm getting at here. As long as P and Q are mutually exclusive, right, this statement is going to be false.
When you say to use a complete sentence,
Mm-hmm.
what do you mean? Like, do you mean altogether this statement is false over this interpretation and then put a domain?
No, when you define your predicate, it has to be a sentence. Right?
Okay, so like X is even.
Yeah, X is even. That's a sentence. That's fine. Right? But all the time, and fair warning, everybody. Every semester, in every class that I teach this stuff, someone always does this without fail. Okay, so fair warning. If you're listening, don't be the one that does this. If you're not listening, one of you is going to be the one that does it. PX equals even, not a sentence. Even is not a sentence. PX equals is even. Again, not a sentence. This has no verb, has no subject, has no direct object. I mean, what is even? It's just a word. It's just an adjective. This has a verb, has a direct object, no subject. That subject needs to be X, or the direct object somehow use X. X has got to be in there somehow. Right? Not a sentence. Again, not a sentence. This is a sentence. This is a sentence. Not a sentence isn't a sentence. What I wrote there, right? So just to further cement that in there. Always use a complete sentence when you're defining a predicate, because a predicate is a statement, and a statement is, by definition, a full sentence, right? Which could be in English just 3 words, right? A propositional statement could be just 3 words. In other languages, it can be even less. But it still has to have that structure: subject, verb, predicate, or subject, verb, direct object. I don't know. I mean, the word for the end of the sentence. Okay. Anybody else? Um, all right. So I'm disturbed by the lack of questions I've gotten over the last couple weeks with this assignment. Again, guys, you have to keep on top of the material to make sure you're going to learn it, because trying to do it all night before isn't going to work. Okay, so back to chapter 3. So we're going over naive set theory, and a set is called is a collection of objects, and those objects are called elements, and those elements are presented in no particular order. Okay, so we write this x epsilon A to mean x is in set A, or x is an element of set A. X is an element of A, or X is in A. X is not an element of A. So in sets, in our example, sets are usually delimited by these brace symbols. That's the beginning of the set. That's the end of the set. Left brace, right brace. And one simple way to express a set is just to list the elements between braces separated by commas. So here's a set with a bunch of numbers in it. All right, here's the same set. This set and this set are the same because the elements are the same. There's no particular order to the elements in a set. Those elements may be presented in a certain order. They may have a certain kind of natural ordering associated with them, but that's not part of what the set is. Okay, it's just the way the set is expressed in the way you're doing it. So, I expressed it like this. You might express it like that, but they're still the same set. So we don't take ordering into account. That's a different concept. And then this is also a set. You can have elements in your expression for a set repeated. If they're repeated, it doesn't mean it's in the set more than once. It just means that the element is in the set, and that's it. It may seem weird to do that. It may seem weird to do it this way, but I mean, with the set builder notation, you often get repetitions in the way of elements in the way you express the set. Okay. There is a concept of sets where elements can be in there multiple times. Such a thing is called a multiset. Again, we're not going to be dealing with that here. Okay, so here's that set again. Notice that 8 is in that set, so 8 is an element of this set. 16 is not an element of this set. You don't see 16 in there anywhere. Elements of a set can be anything. Okay, symbols, geometric objects, and even other sets themselves. So like here's a set, A3, triangle, hexagon, and then this set. So the elements of the set are separated by commas. So after this comma, we see this thing here. That thing there is a set. And then we end the set here. So you could think maybe of these delimiters having different colors. These braces having different colors to kind of separate the meaning of them. But essentially this brace matches with this brace. And this brace matches with that brace. So these two braces express this set. And these two braces express the outer set. So the set has 5 elements. The letter A, the number 3, a triangle, a hexagon, and this set that has 3 elements in it. Right? And so notice that triangle is in that set. 3 is in the set. 3 is also in this smaller set that is within the big set. The square root of 2 is not in this set. This thing is not the square root of 2. This thing is not the square root of 2. This thing is not the square root of 2. This thing is not the square root of 2, nor is this thing the square root of 2. Not that this thing lacks any relationship to the square root of 2. Right? I mean, it does have something to do with the square root of 2, that object, but it is not itself the square root of 2. Right? This thing itself is not the square root of 2. It is a set that has 3 elements in it, one of those elements being the square root of 2, but that's different than the square root of 2 itself. Okay, the square root of 2 is in that small set inside there. And I guess I didn't mention this last bit here. This 3-element set is an element of the 5-element set. So sets can be elements of other sets. And here is where naive set theory gets in trouble. Not that you really have to worry about it too often. because normally we don't deal with these kind of sticky, paradoxical situations. But having sets being elements of other sets, can sometimes get you into trouble with Russell's paradox, right? Okay, but before that, I mean, again, this 3-element set is an element of this big 5-element set. So this set is an element of this set. It's right there. Set builder notation. So a nice way to express sets is with this thing called set builder notation. So when we write this, it's read as follows. This is the set of all, the first left brace means the set of all, elements x, such that p of x is true, and then this ends the expression. So the set of all elements x such that p of x is true. Sometimes you see it written this way. So when things are typewritten, typeset, it's usually done like this. With handwriting, it's usually done with this. Although you can see this done in typeset as well. It's just a matter of preference for whoever's writing. So, for example, the set of natural numbers. This symbol here. So how do you write that symbol? You write the letter N, capital N, and then throw another line down like that. That's the numbers 0, 1, 2, 3, 4, 5, 6, ... So the set of integers, that's all the positive integers, the positive natural number, the natural numbers, 0, and their negatives. Right, so that is the set of all x and negative x. So you can have more than one expression here. The set of all elements x and negative x, such that x is in the natural numbers. Right, so if x is equal to 3, this gives you 3 and negative 3. If x is equal to 17, 17 and negative 17. If x is equal to 0, it's just both 0. And then there's the rational numbers, q. Right, so how do you make that symbol? Just draw a Q and then just add this line here. How do you make this symbol Z for the integers? Well, there's different ways to do it. You can make the letter Z and then just add a line like that. Or more commonly, make one angle and another angle. All right, this is greater than symbol, less than symbol. So the set of rational numbers, it's the set of all elements, a divided by b, such that a is an integer, and b is an integer, and b is not 0. Right? A is an integer, b is an integer, and but b is not 0. So here are some rational numbers. You got 0 in there, you got 5 in there. You have 3 halves, negative 3 halves, and elements in the rational numbers can be expressed in different ways, of course. Right, 3 halves is the same as 6/4, right? So there's repetition in the way that elements are expressed. Not that it makes the element in there more than once. It just means that the element is in there. Some numbers that aren't rational, there's this I, which is the square root of negative 1, pi, the square root of 2, e, this number here. You know what that number is, anybody? It's got a name.
Golden ratio.
Golden ratio, yeah. So some other named sets. So the natural numbers was, right, it depends who you talk to. Sometimes the natural numbers doesn't have 0 in there. It's kind of an annoying distinction. And different people do it differently. I think usually it's got the 0 in there. But if you don't want the 0, then, one way you can say that unambiguously is that's the positive integers. So the integers, and then put a little plus there. Positive integers. And then this, so you put 2 bars and then make an R. That's the set of real numbers. What's interesting there is I didn't define it in any way using set builder notation, and that's because, that's opening up a big old can of worms. um, how do you define the real numbers? It's really something a little tricky. It takes some discussing. That's something you'll do in the real variables class. So there's real numbers. We won't need to do it here. And then there's this, complex numbers. That's the set of all a plus b I being the square root of 1, such that a and b are both real numbers. A is a real number, and b is a real number. So that's using that square root of -1 business, the set of complex numbers. And if you take math 3200 complex variables, you'll go over that. Let's do a couple more examples of set builder notation. Let me see. All right. So another example. So let x, we'll let this set, let A be equal to the set of all elements x, such that x is an integer and -3 is less than or equal to x is less than 7, and x is equal to 2k for some, need more space. No, I could put it down here. Well, let's just leave it at that for now. So let A be equal to the set of all x, such that x is an integer, and -3 is less than or equal to x and is less than 7. Therefore, what? How can we say it without the set builder notation?
X equals -3.
X or A?
Or
Yeah,
A
is this
equals set of -3, 4, negative, or -2, 1, 0, all the way to 6.
Mm-hmm. How about this? Let A be an element, or sorry, let A be equal to, so let's take this set again, and let's modify it a little bit. And x over 2 is an integer. Well, let's call it b this time around. What's b now? I'll call it a again, sorry. What's a now? What are the elements of a? Well, I mean, it's the same as the set before, except I made this new condition. X over 2 is an integer. What's that mean? X over
That means you're including all of the rational numbers between -3 and 6 and 7.
It's gotta be an integer to start with. So x is an integer and x over 2 is an integer. So what's that mean about x? When is x over 2 an integer?
When it's even.
When it's even, right. So only even integers between here and here. So this is -2, 0, 2, 4, 6. Right? All right. How about this? Let A be equal to the set of all x such that x is an integer, again. Oh, no, let's not say that. Such that there exists a y with y an element of the set 1, 2, and x is equal to 2y. Let A be the set of all elements x, such that there exists a y with y an element of the set 1 to 2, and x is equal to 2y. What are the elements of A this time around?
Is it 2 and 4? 2 and 4.
Just 2 and 4. Yeah. All right, so, you know, you using, to obfuscate things completely, you can use this set builder notation, but that's good. You guys got through that right away. All right. So that was set builder notation, but like I was saying, with naive set there, you do get into trouble when you can say, sets can be elements of other sets, because then you run into the problem with, a set being an element of itself. Kind of like this thing here, right, on my OBS Studio. Right, I mean, it shows right here, right, it shows, this is my screen.
The tunnel.
Yeah, that tunnel thing going on, right? And then this is the OBS Studio, which shows my screen, which has got OBS Studio showing my screen, is such an image really possible? Well, since we're dealing with finite pixelations, it's not infinite. It doesn't continue on infinitely like that, but this is kind of related to that. We have said sets can be elements of other sets, and this leads to Russell's paradox. Let X be the set of all sets B, such that B is an element of B. Let Y be equal to the set of all sets B, such that B is not an element of B. Where is Y? Is Y an element of X, or Y an element of Y? Every set, either, given any set, either it is or it is not an element of itself. So, of course, for any set B, either B is an element of B or B is not an element of B. Right? Either it is or it is not. It's one of these dichotomy things. Either it's in there or it's not in there. But then the problem is, what about Y? Is Y in X or is Y in Y? Well, if you said that Y is in X, if Y is in X, that means Y is an element of Y. Well, therefore, by definition of y is not an element of y. If y is in x, then by the definition of x, y is an element of y. Right? But for y to be in x, wait, hold on. Is y an element of x? If y is in y, that means y is not an element of y. Right, so if y is in y, then by the definition of y is not an element of y. That's contradictory. If y is in x, also, so if y is not an element of y, then y is in x. Let's rewrite that. If y is not an element of y, then by definition, always does that. Sorry, I have to close this and reopen it. If y is not an element of y, then by definition of x, then y is an element of x. Thus, y is an element of y. Contradiction. So, this notion, these sort of freewheeling notions in naive set theory, they lead to these inconsistencies. So there is a set theory which is on a firm logical foundation, but sorry, not a firm, a consistent logical foundation. But then there's other problems with that. I mean, the logic runs into all kind of weird problems later on. But that's not something we're going to touch at. But this is not something you really need to worry about, but it's something neat to think about. All right. For the most part, everyone ignores formal set theory. Except for logicians and set theorists, and sometimes analysts. Subsets. So we say that A is a subset of B. So it's kind of like less than or equal to, except it's rounded. So this is read as A is a subset of B when the following predicate logic statement is true. Over the whole over a domain containing both A and B. So for every x, if x is an element of A, then x is an element of B. So x in A implies x is in B. So, as I was talking about right from the very beginning, implication, right, as a logical construction, as a logical connector, it really is a description of a containment relationship. Which containment relationship am I talking about? Well, it's this subset relation. Like, if this is a set A, and this is a set B, right, and A is contained in B, what does it mean? Any element X that is in A is also in B. If the hypothesis here is true, then the conclusion has to be true as well. In this picture, right, this means A is a subset of B. Here, it's not true. if this is A and this is B. And this is X right there. Right? This X right here is in A, and X is not in B. Right? And let's see, I think I'm gonna get another page. This is too cramped. So in this picture here, let me make it bigger. A is not a subset of B because there exists X such that X is in A and X is not in B. And there it is right there. Right, when is an implication false? When is an implication false? The only time an implication is false is when what?
The hypothesis is true and the conclusion's false.
Hypothesis is true and the conclusion is false. Hypothesis being true means we've got some X that's in A, but X is not in B. Right? Not that there aren't any things like this, like that's X and then this is Z. Right here, this Z is an element of A, and it's an element of B. Right? So it doesn't make this false, but there is something that does make it false. Right? Subset means for every element, X in A gives you X in B. Here, well, sometimes X in A gives you X in B, but there is a thing that is in A, but not in B. So hypothesis true, conclusion false. So the implication describes exactly this containment relationship that we've been talking about. Right, this subset relationship, and that's why I just sort of introduce it right off the bat, because I mean it's something that's intuitively clear, this subset concept. All right. So for example, like if I had this 1, 3, 5, 7, 9, that set there, well, that for sure is a subset of. Excuse me. That is a subset of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? Any X that you pick here is also in here. It is not possible to pick an X in here, but not in here. Right? Picking an X here gives you an X here. So X an element here is true. Always gives you X an element here is true. So that's the logic of it, but I mean, the intuition is just, well, the elements here are within the elements here. For any set A, right, that's always true. Any set is a subset of itself, right? Because if X is an element of A, then X is an element of A. They're actually equal, right? But it doesn't make this false. Is that false? A is always a subset of A for any set. You might be tempted to say, yeah, that's not true. Why would you be tempted to say it's not true? It actually is true from a perspective of formal logic, but why would you be tempted to say it's not true? Or why might you be tempted to say it's not true? Because it doesn't what? It doesn't tell. So but in a journalistic sense, it's bad journalism to say A is a subset of A, right? Because in journalism, you want to tell, right? You want to tell a story, and you want to tell the whole story. You don't want to leave stuff out. Like, and as much as possible, you want to tell the whole story. I'm sorry, it's time to go. It doesn't tell the whole truth. A is actually equal to A, right? It doesn't tell you the whole truth. Doesn't mean it's false. It's just a half truth, so to speak, right? But a half truth is a truth in formal logic. And they have their usages. All right. So